We're going to do this problem. It would really be helpful on your AP test for response questions. They a lot of times have questions that look like this, and they give you this function. This graph right here is f, and they give you this for g, and they ask you a whole bunch of questions related to g. So if I want to do this, if I want to find, let's start off with g of 3. What that means basically is if g of x equals this, g of 3 would be simply, the integral from 5, since x is 3, from 5 to 3 of f of t dt. And from there, you should realize, okay, this is saying find the area of f from 5 to 3. Now my integral is backwards, so hopefully you realize, because the interval is backwards, you need to make this a negative and switch it from 3 to 5 of f of t dt. Now, from there, again, we switched it because the interval is upside down. How do you find the area from 3 to 5 of this graph? Well, we're going from 3 to 5. So you're going to go from 3 to 5, and we're going to find the area of this shape. And if you think about it, you can think of it as a trapezoid or of a rectangle and a triangle. I think of it kind of as a rectangle right here and a triangle, and you would catch on that this would be an area of 3. Now, your answer for the area is 3, but negative means opposite, so it would be negative 3. So that would be g of 3. You simply do the integral. Now, what if I want g prime of x? Well, if this is g, I want g prime of x, that means I'm going to derive that, which also means I'm going to derive this. So when I derive this integral, when you derive that, what you need to realize when you do this is that, again, when you derive this, you derive the other function. When you derive this, this is called the second fundamental theorem of calculus. So what you basically run into is g prime x is actually equal to f of x. Because the second fundamental theorem of calculus says when you derive an integral in this form, you simply take the x and plug it inside, and that's your answer. So you have to know the second fundamental theorem of calculus. It saves you a lot of time. When you derive g, you derive the other side, and so g prime is simply f of x. So if I want to find g prime 3, well, that just means, if g prime equals f of x, g prime 3 is simply going to be f of 3. And if this is f of 3 is simply that dot right there. So at 3, the function of f is 1. It is 1 high. There's my answer. Now, that was negative 3. So it's pretty simple, as long as you know this thing right here. This is the building block for the whole entire problem. Very important. Now, for the next problem, g prime, double prime. Well, if g prime is f, g double, when you derive this, you also derive this. So won't this simply be the first derivative of f? So the derivative of this means I also derive this. So the second derivative of g is the first derivative of f. And then you're going to use this for a lot of problems as well coming up. So the second derivative of g is the first derivative of f. It's kind of weird for people to wrap their head around. So anyways, if I want g prime, double prime 3, the second derivative of g at 3, I want technically the first derivative of f at 3, which hopefully is a lot easier. So if I look at f, that means the slope at 3, the slope of this graph at 3. So at 3, what's the slope of this line? Well, if you think of slope, isn't it rise over run? So didn't I go up 1 over 2? Up 1 over 2. So my slope is 1 over 2. 1/2. So the second derivative of 3 is 1/2. That's the first derivative of g at 3 is 1. And this right here was just the function at 3. So the key here is, again, noticing this and then deriving it and then deriving it again. And once you know these two things, you're doing really well. All right, next piece. I want to find, where is it decreasing? What you have to imply when you hear the word decreasing is very important. Decreasing means when g prime x, when g is decreasing is when g prime x is less than 0. Meaning, when I say g decreasing, the moment I say decreasing, I'm saying derive g and negative. If I said increasing, I say derive g and positive. So this is deriving g and making it negative. Less than 0 is negative. Now, we have to remember this stipulation right here, all right, that g prime equals f of x. So let's write that down again, that g prime x is equal to f of x. So if that's true, if I'm going to find when g prime is less than 0, and I know g prime is equal to f of x, can I then state that I'm looking for when f of x is less than 0? Since g prime equals f of x, aren't I looking for basically when f of x is less than 0? So if I look at my graph, when is f of x, when is this function less than 0? Meaning, when is it below the x-axis? And what you notice is, oh, it's below the x-axis from 0 to 1. So it's on the interval 0 to 1. And, oh, it's also below the x-axis from 6 to 8. On the interval 6 to 8. Those are the two intervals. They're not coordinates, but intervals for which we are decreasing. And here's my stipulation, which this leads to this, and so these are my two decreasing values. It'd be increasing right here, because those values are above the x-axis. Okay, next, when is g concave down? When I think g concavity down means second derivative negative. So I'm basically looking for when the second derivative of g is negative, concave down. Okay, that's useful, but what we first got to do is go back up to here and remember that, okay, g double prime x is equal to f prime x. So what that leads me to think, okay, instead of thinking this is g's, let's think of it as f's. So this would be f prime x. Instead of this less than 0, what about that f prime x less than 0? So instead of thinking of g double prime, meaning the second derivative being negative, how about do the first derivative of this graph? And when I think of first derivative, you should think, okay, first derivative means slope. So I'm thinking slope of f negative. So where do we have slope of f negative? Well, look at this graph. The slope here is positive, slope's positive, oh, slope's negative, slope's positive. So the slope of f for this interval is negative. So that'd be from 5 to 7. So my answer is from 5 to 7. Now, if I want concave up, that would be where my slope is positive. Slope positive and slope positive. Again, decreasing was the first derivative, negative. Concave down is second derivative, negative. You have to be careful of that, and you want to put both of these in terms of f, because f is what we have a graph of. We don't have g, so you got to keep changing everything to f's, like I said up here. Change everything from g to f. It gets kind of confusing, and I'm sorry. These can take a little bit to get used to. Anyways, next one. Where are the point of inflections? I call them P of i's. Now, the definition of a point of inflection is basically, again, the definition of a point of inflection is when the second derivative equals 0 or does not exist. That's the first part of the definition. The second part of the definition of a point of inflection is that it changes concavity. So we also have to change concavity over the point. So you have to have the second derivative equals 0 or does not exist, and has to change concavity. Okay, so the first thing we want to do is we want to go back to this idea right here. Okay, I got to remember, okay, g prime x is equal to f prime x. So if I want to find out, okay, when is g double prime x equal to 0? That means it's when double prime, so when f prime, or the derivative, is 0. So let's look for this. When is this equal to 0? Okay, remember this, and this is what we're looking at. So we're looking for when the first derivative equals 0. All right, so the first derivative equals 0 means when's the slope 0? Okay, so looking at this graph, when is my slope 0? Oh, sorry. Or does not exist. So when I look at this graph right here, f, where are my slopes 0 or do not exist? What I notice is, oh, right there, my slope does not exist, because at jagged points you don't have slopes. So at that point you don't have a slope, and right here you don't have a slope. So where is this? It would be when x equals 1, x equals 5, and x equals 7. Those are my values where I do not have a slope. The slope does not exist. Now, does that mean it is a point of inflection? No, because I have to check that concavity changes. So let's check which one of these. So let's look at the concavities. We already checked the concavity here. So we have to check the concavities. So for the concavities, we want to check where the g double prime x is less than 0. So where is it less than 0? That's what we did up here. So it's less than 0 from 5 to 7. Where would it be greater than 0? Sorry, g double prime x will be greater than 0 on the other intervals. Remember, g double prime is the slope of this graph. So the slope's positive, positive. So for that interval, it's from 0 to 5, and then from, it's also positive from 7 to 8. So those are my intervals for where it's positive, going uphill. This is where it's going downhill. So if I look at this, if I look at my thing, okay, that means that at 1, actually my slope was positive and positive some more. So is 1 a point of inflection? Actually, no. It's not. Is 5 a point of inflection? Yeah, because I go from slope positive to slope negative, so that's a point of inflection. This is slope negative to slope positive, so that's a point of inflection. But that one's not because I go slope positive, slope positive. So the slopes don't change concavity because they don't change from positive to negative or negative to positive. They don't change signs. So this is my explanation showing the information. This is all good for reasons why. And so my final answer is basically, where are my P of I? Well, my P of I are going to be x equals, let's see again, it was 5 and 7. Those would be where my points of inflections would be, at 5 and at 7. Again, it has to change concavity, and this is your stipulation to start with. All right, next one. Quantify absolute minimum values. For an absolute minimum, we have to check endpoints and any relative max and mins. So if I want my endpoints, I need to first find my endpoints of g. So that's g. So g of my endpoints would be 0, and I also need g of endpoint would be 8. So we're going to find both endpoints, and we also got to find relative maxes and mins. So to find g of 0, well, doesn't that mean you just use this formula? So you're going to take the integral from 5 to 0. It's getting kind of small. Sorry about that. And isn't this one going to be for g of 8? Isn't that going to be an integral from 5 to 8? And we're integrating. Doesn't that mean area under the curve? So basically, from 0 to 5, I want the area under the curve. Now remember, the interval's backwards, so we're going to change the sign. So technically, this one's going to be the opposite of what your answer is. So the area from 0 to 5, well, that was 3. If you look at this little, that's 3. We already marked it. This is a box of the triangle, base 2, height 1. Area is base times height divided by 2. So this is 1. This one's area is 1 by 4, so 1 times 4 divided by 2. This is going to be negative 2, because negatives below the x-axis are negatives. If we look at this one, this is 1 by 2, so this is a negative 1. This is a positive 1. And the area of this one is 1 plus a half, so it's negative 1.5. So those are all my areas under the curves. So anyways, if I went from 0 to 5, or 5 to 0, that'd be 3 plus 1 is 4, minus 2. So we got 4 minus 2 is 2, but I want the opposite of that. So it's going to be negative 2. Again, it's the opposite because the interval is backwards. That's a negative 2. Again, 4 plus negative 2 is positive 2, opposite. And if I went from 5 to 8, 5 to 8 is, that's good, the interval is not backwards. 5 to 8, so 1 plus negative 1 is 0, plus a negative 1.5. So 0 plus negative 1.5 is negative 1.5. So those are my endpoints. So as of now, if I stopped, that would be my absolute min. But what I also have to check is any relative maxes and mins. So I need to now find my relative, sorry, not maxes and mins, I need to find my relative mins. So let's look for relative mins. Where would they be? Well, the stipulation for relative min is that the derivative equals 0 or does not exist. And then using the second derivative test, we also need to verify, I'm going to use the second derivative test, that the second derivative at that point would be, for a minimum, your concavity would be up. If you think of a minimum, it looks like this. So the concavity would be up. So if my second derivative, I want it to be, for concavity up, I want it to be positive. So I'm looking for where equals 0 and the second derivative is positive. So let's look where the g prime equals 0. Now when g prime equals 0, go back up here, g prime is f of x, so we're basically looking for when is f of x equal to 0. Well, f of x is equal to 0, let's see here. F of x is equal to 0 right there and right there. So my two possibilities for f of x equaling 0 are x equals 1 and looks like 6. Now which one of these would be a min? Well, it's where g double prime is positive. So that would mean if you're deriving this, it would be where g f of x, I want it where it is also positive. So if I look at 1 and 6, when I look at 1 and 6, I'm looking at the slope. So at 1 and 6, if you look at the slope at 1, do you understand that actually the slope does not exist, so we can't actually use second derivative test? Darn it. We can't use second derivative test, so that does not help us, because technically at this point it doesn't exist, so I can't check if it's positive. Darn it. Second derivative test can be helpful, but it doesn't here. So technically this is not going to help. That was a good catch. Now, since those don't work, okay, I got to use first derivative test. So I got to check over the interval. I got to see if it changes from for a min. For a min, we want it to go from, what I'm going to want is g prime. I want g prime x. I want it to go from, for a min, I want to go from decreasing to increasing. For a minimum, it goes from decreasing to increasing. So I want my derivative to be from negative to positive. So if I look at these, which one has negative g prime, which would be f of x, which goes from negative to positive? And when you look at this one, you will notice, oh, at 1, doesn't it go from negative values to positive values? This one goes from positive values to negative values. So 1 is your relative min. The reason relative min, your relative min is 1. That's your relative min. And the reason is because g f of x is less than 0 on the interval 0 to 1, comma 1, and f of x is greater than 0 on the interval 1 to, it doesn't really matter, 6. So what happens is, as you see, because of this information, we can know that's a minimum, again, because you go from negative values to positive values. So we know, we verified that's the min. Okay, all that. How do I know it's a min? I know it's a min. Now how do I check that? Well, I now have to check that value, actually. So to actually find that value, what I now have to do is I have to actually find g of 1. Now g of 1, just like we did over here, is from 5 to 1 of f of t dt, because we know 1 is a minimum. Let's plug this in. And when I plug this in, my area from 1 to 5 is 4, but the opposite of that would be negative 4. Now we look at all these values, which is the smallest? What you'll notice is this is the smallest value. So what we know is at x equals 1, you have your absolute min. All right. A little bit kind of difficult to see that, but you will get it. All right, the last one. The last one here. What is the average rate of change? The key is the word rate of change of g. Now, rate of change means the derivative of g. So the average rate of change, when you average, here's what it looks like. If I want average, average is 1 over the interval is from 0 to 8. So it's 1 over 8. I'm going from 0 to 8. And I'm averaging rate of change, so that I'm averaging actually g prime x. So average rate of change, here's the word average. You're going to do this average integral. But rate of change means the derivative of g. So to calculate this, what we got here is, okay, I can integrate this, because when I integrate this, I keep the 1/8 in front. And that leaves me, oh, the integral of g prime, isn't that just g? And don't we plug in 8 and 0 for the integral? So what this actually becomes is 1 over 8, and this becomes, oh, g of 8 minus g of 0. Okay. Oh, hopefully that's reasonable. G of 8, look at my function. I have it right here. G of 8 and g of 0, they're right here. Oh, cool. So if I equal, I've got to come over here. Won't that be, okay, I have 1 over 8, and g of 8, again, is, oh, negative 1.5, minus g of 0 is negative 2. So when I do that, oh, negative 1.5 plus 2, isn't that going to be 1 over 8 times, it looks like 1/2? So it to be 1 over 16. So my average, it looks like, my average rate of change is 1 over 16. With these problems, be very careful, think through the whole thing. I kind of went fast. The key is changing all my g's and thinking of, for instance, g prime is f of x, g double prime is f prime x, and thinking through this. This also correlates to other types of problems. Hopefully this helped you.